This is something we would present to venture capital, but we do believe we are today probably a first of a kind in terms of bringing advanced phase change materials fully to market in the context of a device that you can just buy. You can phone us up today, you can order one and it'll be shipped to your house and an installer can install it day after tomorrow. And you know, lots of promise of this for a long time. Now it's here. We very much have built our company to align with the transition. It wasn't called the transition when we started, but it is, I think, called the energy transition now, and it's a good thing. And we started it partly because we reject the thesis that we should all accept climate change. We should change it. We should change the basis of our energy system and move beyond that. As a result, there's obviously a huge addressable market. The today market is denominated by things like hot water cylinders, hot water tanks. The future markets are much more about accepting converted renewable energy, storing it in the form of heat, and returning it in the form of heat or cooling for different applications. You'll see something about product competitiveness, but let me just summarize right now and say we have products today that you can buy for the same price as water tanks. So therefore, we think we're competitive. And in fact, when we speak with people who are the main adopters for us, which is people like house builders, they're saying, yeah, actually, you're a little bit more expensive than a water tank, but not much. But you buy us a lot of value that we like. Management team and board I'll talk about, and the fundraise is immaterial probably to this discussion today. So why are we doing heat energy storage? Basically because the world uses, in final energy consumption terms, much more thermal energy than anything else. And yet the focus is usually into that corner up there, and now increasingly into that piece there as well, with electrification of vehicles and so on. But we think this bit has tended to be the forgotten topic. So we decided to go there. And we also thought that if we were going to build a business, electrical storage just had too many people piling into it with too much money, and actually too much money needed to do the job. Whereas heat storage, I would argue, hasn't really changed in centuries. I would argue that any Roman citizen would understand hot water tanks and would understand, I mean ancient Roman citizen, would understand hot water tanks and actually hot brick storage, which is night storage heaters, electric thermal storage for the North Americans amongst us. They would understand that apart from the electric bit perfectly well, because they had hypocaust. They had bricks that stored heat. And the amount of storage is going to go up and up and up. I'm not going to talk about our management team, but the reason for putting that up is twofold. One is to say we're very much at the commercialization phase. All of these people are heading up business units to commercialize things in different areas like commercial, industrial, automotive, and for this topic, probably most importantly, domestic scale, these two. But we also view our science base as a critical part of our management resource. And in fact, although Professor Colin Pullen doesn't have a formal position with the company, his influence on what we do from his position as head of School of Chemistry at the University of Edinburgh is of great importance. And his first combined with us industrial PhD student, who now got his PhD a while ago, Dr. David Oliver, as our head of materials, they are incredibly important to what we do. And in fact, these people up here couldn't do anything if we hadn't developed technology together that we can commercialize. And recently that was recognized in an award last week, the Scottish Knowledge Exchange Awards. We won the Powerful Partnerships Award, and there's Colin, David Oliver, Dr. Kate Fisher, Dr. Rowan Clark, and Emily Goddard, who is doing a PhD. These three with us, Kate independently, but has joined us from the University of Edinburgh. So it's a strong team, and there's a lot more people besides that. And I'm afraid I don't give full credit to everybody at every point through this, as other people have done. I liked what you did, but we're not academics, so we may not actually cover it in quite that way. What is the idea? The idea is basically to harness phase changes, so latent heat, and turn it into a device. So you see a third generation device on the right, sorry, on your right, yeah, on the right. The way we build that is we start with material which is essentially the same as is in a hand warmer. And in fact, I have brought some hand warmers here, and we're going to hand some out. So we make it interactive at this point. So let me give you that, as we agreed. So we're talking, I mean, I'm sure this is all obvious to all of you, but we're talking about solid, liquid, and liquid-solid phase transformations. And these are a nice portable demo of that, so I had a few brought down, and you can all have a play. This is actually, the liquid is in a supercooled state. It's about, here today, 40 Kelvin below its transition temperature. Maybe slightly over that, maybe 35 Kelvin below the transition temperature. You can actually cool it to, I think, about minus 26 Celsius, and the phase transition is 58 Celsius, so you can go more than 80 Kelvin below the transition point, and it will not freeze until you introduce a seed crystal. And introducing that seed crystal is what the little clicking disc inside. So if you have the little clicking disc here, and you manipulate it, you sort of try and invert it, try and make convex become concave, or vice versa, you will then have a nice demonstration of releasing the latent heat from the transition, the recrystallization. So that's great, and these are everyday objects, and we don't make these. We buy them from a factory in Shanghai who make them as promotional articles, and they said in one campaign in Japan 6 million of them have been given away to people at golf courses. So, you know, these are widely available. We're not trying to claim anything new about this. And in fact, in Cambridge, in the chemical engineering school, and I should have remembered the names, but I don't just now, there was a very nice set of 3 papers written about actually the probable mechanism by which the clicking disc works, and other features of these, and if people want the reference later, I'm happy to share it. But it's not kind of useful by itself. It's useful if you're going for a walk or golfing or skiing, but it's not so useful if what you want to do is to make something that would replace a hot water tank, which would have pipes going into it and a heat exchanger inside, because you want it to crystallize reliably without having to have that little clicking disc, and you also want it to be stable over the long term. And this is not stable over the long term. It will probably cycle 100 times before it starts to degrade, and I'll explain why further on in the talk. So we want a material that is stable and reliable. We want something that is going to deliver high power. And to be honest, for that, we didn't adjust the material. We tried, but it's a losing game. You can maybe treble or quadruple the thermal conductivity from its 1 watt per meter Kelvin up to something like 4 watts per meter Kelvin by adding things to it. It's not enough. So instead we put in a highly finned heat exchanger, which we source from conventional sources. And then we also wanted to be extremely energy efficient. So much to my engineer's horror, I insisted that it was going to be flat-sided and not cylindrical. So our cylinder equivalents are cuboid, because then we could put vacuum insulation panels around them. Vacuum insulation panels tend to come in flat sheets because of the way they're made, and it's much cheaper if you do it that way. So we, as a result, have a very energy efficient thing. And it's scalable, modular, and so on. What am I doing? Doing the wrong thing. So latent heat, just a quick historical reference, 1761, it was Joseph Black who deduced that the energy must be going somewhere when ice was melting. And he coined this phrase, latent heat, hidden heat. And we utilize that today. There's lots of compounds that you can use. Some have been mentioned already today. And here's just a small sample, of which the one that we're interested in mainly in our work is this one here. And they have different good points and bad points. So the organic materials are attractive potentially, but they're quite low density. quite low energy density as well as physical density usually, and they're almost invariably flammable, and we don't view that as being highly desirable when you're putting it into domestic scale stores. Salt hydrates are fantastic in many ways in terms of energy density, but typically have very unstable melt-freeze behaviors, and we need more than 10,000 cycles to create a usable device with a long life. But the win, if we can get it to work, is this really long freezing plateau where we get energy out at the same temperature, and that isothermal property is useful. Here's some other properties that are useful. Being in the right temperature range, a small volume change, didn't even put that on there, but that would be another thing that would be a useful property, and so on. And what you find is that you start with this giant database of millions of materials you could choose, and after a while you're down to a very few that could potentially be okay. And in fact, most PCMs, most phase change materials on the market tend to fail some of these tests. Usually stability, usually flammability or toxicity. There's some companies that have tried to commercialize barium hydroxide octahydrate. It's lethal in tiny doses. Don't go there. So it becomes essential to map, understand, and control crystallization processes. And here's where we actually get to start doing a little bit of science. So we've got some general problems. Corrosion is one. You can see here we've got a contact with the heat exchanger the heat exchanger is gradually corroding into the phase change material. It didn't start green. The green is copper or copper salts. A big one is incongruent melting, and I'm going to go on and talk about that one in a bit more detail. So, phase diagram. We've got temperature running along here. Sorry, temperature running up here. Percentage of salt and water running across this way, and we've got the ideal point. The trihydrate point is here. Problem is when you melt it, you raise it in temperature, it's solid, 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 and it now starts to melt. What you get is a liquid solution and anhydrous, and the anhydrous salt happily sinks to the bottom of the vessel and will sit there and not redissolve very easily. In fact, you'd need lots of agitation to make it redissolve. We want a passive device. We don't want motors inside it and stirring bars and so on. Okay, so how about we increase the amount of water. We add extra water, this extra water principle. Plus about 4% extra water moves you across to this purple here. So now you get a clean transition between the 3-hydrate plus a bit of extra water as a solid roughly at the expected melting point. You get a transition to a full liquid solution. Great. But this is what that curve looks like when you recrystallize it. It's rubbish. I mean, it's probably what's in here. Okay, let's we've never actually analyzed it, but these are almost certainly have lots of extra water, 4, 5, 6% extra water, so they last for a while longer. Even then, because you get concentration gradients and so on, actually they're not going to last forever, even if you add extra water, because some parts of the system will end up being over-concentrated, will be over here, anhydrous will fall out, and the system splits. Incongruent melting. There's been lots of other approaches around polymers, so let's thicken it so that the anhydrous stays suspended instead of falling to the bottom. Cellulose type approach, wallpaper paste if you like. Honestly, they don't work for a long time. They work for a short time. So our approach, I had no credit for this at all. These guys had the credit. The approach was, let's develop a crystal habit modifier. Let's go and search for a crystal habit modifier. That means that the anhydrous formation is fully suppressed. In a moment you're going to ask, how do you know? I'll tell you about that in a moment. But in the short term, there's a polymer. It's a sodium salt of, I forget which polymer. But anyway, there's a sodium salt solution of a polymer which is soluble. and it causes the suppression, the full suppression of the formation of the anhydrous at an optimal concentration of essentially 3 moles water to 1 mole of sodium acetate. Fantastic. We get a lot of good results from that. It's workable, it's properly liquid. When it's liquid, it's optically transparent, the storage capacity is great, we don't get any degradation. And those are the key things. And as a result of that, we filed some patents under an IP sharing agreement with the University of Edinburgh, and the papers have been delayed, and we apologise to the academic community. The patent system kind of forces you sometimes to be antithetical to good science, but we're going to get on now with publishing all of this stuff so that it's widely available. You can read it all in the patent literature actually now. So how do we know it? How do we know what we did was good? Well, because we had this amazing ability through our academic collaborator, and I commend all SMEs, if people are watching on the stream, get academically collaborating, because it gives you access to thinking that you wouldn't have. I know you guys know this, but thinking that you wouldn't have, and also facilities you wouldn't have access to. So this is the Diamond Light Source, a sort of football stadium-sized synchrotron in the Harwell campus in Oxfordshire. There are several around the world of this scale. You're spinning electrons around in a ring, essentially. Every time it's a polygon. Every time they turn a corner, you get a huge Bremsstrahlung, a fantastically strong X-ray source, and you have these beam lines. And we're on the I11 beam line, able to put some material in a capillary and heat it and cool it while taking an X-ray crystallogram of high resolution every 8 seconds. Now we can see what's actually going on when we melt and freeze the material at the crystallographic scale. And that was fantastic, because what it meant was we could do a number of things. First of all, we needed I should have mentioned this. We needed a nucleator as well. We didn't want that little clicking disc. So there's also a nucleator. And we had multiple theories as to what nucleator was which. It was a phosphate, and we weren't sure which phosphate was the important one. So we had a mix of phosphates in there. We could see exactly which phosphate was creating the nucleation effect. Great. But the key thing was we could see that sodium acetate anhydrous forms when you cycle the material with no polymer. When you add the polymer, sodium acetate anhydrous does not form during the melt-freeze cycle. So we kind of had a science result 4 or 5 years ago that said our engineering result, what engineers want to see is they want to see cycle tests. We knew the cycle test result from the science before we did the cycle testing. But we still did the cycle testing because there's other people that want to see cycle testing. So this is our cycle testing. This is about 3 years worth of data. And it goes out to 40,000 cycles. So a cycle is go from 40 degrees C through the phase transition at 58 to 80 degrees C and come back down again. And that's in a device this scale, so a 32 kilo heat battery with a heat exchanger in it, cycling every 15 minutes, there or thereabouts. A 2.25 kilowatt hour nominal capacity device. So 2.25 kilowatt hours is this line over here, midway between these two grid lines. Of course, it actually starts with a higher capacity, and these are the data points. These are taken out of high resolution scans every so many cycles, and the green are normalizing it against factors like differences in the mains temperature and so on. We weren't using a lab, we were using a factory to do this testing, with scientists running it. So actually we've got about 48 watt hours of reduction per 10,000 cycles. If you fit a straight line to it, it may be that we shouldn't be, maybe we should be fitting a curve. If you took the early part of the curve out to about 20,000 cycles, the rate was about 25 watt hours, sorry, milliwatt hours per cycle, watt hours per 10,000 cycles, on a device which is 2,250 watt hours of capacity. So you've actually got, you can go 40,000 cycles and get a less than 10% degradation. If I could do that with lithium ion, I would be one of the richest people in the world today. Right? So just to give you an idea, it's a good result. Actually, we can we can fix it. All that's happened is some water vapor has left the system. We can just put some water back in and we'd be back to full capacity again. But we've got a sealed device. You can open it if you really need to service it. We've got a sealed device that will last probably 100 years. Sorry, I forgot to turn on the timer. How am I doing for time? Somebody needs to give me a time check here.
Yeah.
Okay.
So you are scheduled until 2:20.
And what time is it now?
It's 2:15.
Okay, great. So I'll not say some of the other stuff. In fact, I'm kind of maybe just going to stop there and say, you know, we got a great result from the science. It allowed us to go on and build a product range. It allowed us to go and build a business on that, so that today we have products, and those products are, as I say, out of the catalogue. You can go and buy them, and we couldn't have got there without the science base. And we continue to want to collaborate. We have, for example, and you'll see it here, a large range of other materials in various stages of development, and there are many more targets that we're interested in at lower temperatures, at intervening temperatures where there is nothing good for us at the moment by our criteria, and at higher temperatures, yeah, for many applications. So, yeah, thank you.
Thank you very much. With time for questions. Yes, please.
So you mentioned early on about the heat transfer issues, and I think you mentioned you can get up to 4 watts per meter Kelvin, which is not good enough. How high does it need to be good?
10 to 20 would probably be good enough for cheap heat exchangers to be used.
And could you do that with additives, for example, adding in things which are more...
So that 4 is with additives, things like graphene.
Okay.
Yeah.
Try that.
But if you know something better, we'll talk.
I see many applications here, but I don't completely understand where the heat comes from originally.
Yeah. So the other part, if I timed myself better, we'd have been talking about heat pumps for a little bit. So let me jump through very quickly. So the heat can come in from multiple different places. We can just literally put grid electricity through a heating element inside. We can bring heat in from a boiler, which is fueled normally. We don't like this fossil fuel stuff, but you know, it's the world that we live in today and hopefully transitioning out of rapidly. It can come from PV or solar thermal. It can come from heat pumps. And we've got a lot of great experience running these with heat pumps, and the net result of that is that you can have space heating and hot water at roughly half the cost in the UK market of heating and hot water with a gas boiler. Half of the benefit comes from the COP of the heat pump. Half comes from the fact you've got storage that allows you to time shift to when the electricity is cheap. So it's like night storage heaters, but with the COP of a heat pump. I hope that, I'm sorry that's a very quick summary, but hopefully that's clear. Yeah.
I wanted to ask about the equivalent of leakage in the other case. So you do insulate these things, and if you stored 100 kilowatt hours, whatever.
Yeah, whatever the number is.
What percentage would you use in 12 hours or 24 hours?
Okay, well luckily I have a slide to that as well. So this is according to the ERP, Energy Related Products Directive, running their standard test. Essentially it gives you the 24-hour heat loss. So if I take a unique HW9, which is the equivalent of a standard 210 litre cylinder, it loses 0.738 kilowatt hours per 24 hours through the walls. Now, the other thing you could have done is you could have subcooled and said, I'll sacrifice some specific heat early, but then now I have a storable material forever until I activate it. But actually on diurnal cycles, multi-day cycles, it's not worth it. Your heat leakage rate is really low compared with the loss in that losing the specific heat, which you have to make back up essentially by recrystallization. So turns out this is the right way to do it for diurnal stores. For seasonal stores, you would do it the other way. You would use the subcooling and recrystallization. And actually, there's also a slide here that shows the difference between if you have a tank already and it's 10 years old, it's probably losing a megawatt hour of heat a year, there or thereabouts. And we would lose a quarter of a megawatt hour per year, there or thereabouts. So actually, it's you know, it may be worth looking at your old tanks and thinking about replacing them. Sorry for the pitch.
Any further questions?
Perfect.
Okay, so thanks.
Thanks.